What the heck?
Tagon.
It's hot. So, today for our next episode of
Monday Math Nuggets.
Yeah. What are we doing? I'm just going to be doing two stupid little things that I thought were interesting. Stuff that I don't think I'll be, like, trying to investigate, like any hang on. Excuse me. It wasn't the dog. The dog's not here. I did that. So, just show you two little interesting things that I would encourage people in my audience to try and investigate themselves, because this is nothing I'm going to be like going into detail on. I'm just going to throw these things out there and see if anyone's interested in maybe exploring them further as little mathematical nuggets. And the videos that are going to come out after this are going to be on the Bernoulli Numbers and the Euler Summation Formula. I'm finally getting to this. Somebody sent this to me via email a long time ago, and I never got around to it. And it's actually interesting that I'm doing this because Papa Flambam is doing videos on these weird joules, like crystalline fractions, like fractions and fractions and fractions. And he's going to do it involving sums of powers of integers as opposed to just sticking with the sums of integers that he's doing, which I think is a really, really neat idea. I'm probably going to explore some of it myself, and he's going to need the Bernoulli numbers for that. So if you're interested in continuing to watch his series and want some background, then watch the series that I'm going to have coming out this week about the Bernoulli numbers. Oh, and Papa, where the f*** is your response? All right, let's get to the little nuggets now. So one of the little facts that I wanted to take a look at was something that I didn't realize was so easy to consider, and that would be derivatives of the Riemann Zeta Function, which I think would be pretty cool to take a look at. So, remember the definition of the Riemann Zeta Function is just this lovely little sum over negative powers of the integers, which I think is just a neat little idea, which is actually tied into the whole idea of Bernoulli numbers, so we're going to be getting into that later as well. But let's take a look. So the Riemann Zeta Function, written with capital Zeta, usually of S, where S is a complex number, is equal to the sum from k equals 1 to infinity of 1 divided by k to the power of s, where the real part of s is greater than 1. So the real part of s has to be greater than 1 for this definition to hold. Of course, there are the analytic continuations of the Riemann Zeta Function, and they're all well and good, but that's not in the purview of this video. So what we're going to do is we're going to take the derivative of the Riemann Zeta Function. So we have the first derivative, and I will be using this derivative index notation like that. Well, because this is with respect to x, we have to think, well, what's the derivative of, you know, an exponential function in s, right, where s is the variable? Well, of course, it's simply going to be the natural log of the base times the function. But of course, this isn't just k to the s, it's k to the negative s. So what we're actually going to get is the negative natural logarithm of k times k to the negative s. In other words, negative log k divided by k to the s. Now, if we kept going, you know, taking more and more derivatives, all that would happen is that we would just get, why do I keep all my pens here? All that would happen is we would just get successive powers of the negative natural logarithm of k. So if we kept taking derivatives, we would end up with the nth derivative of the Riemann Zeta Function equals the sum from k equals 1 to infinity of negative log k to the power of n divided by k to the s. And now what I did, just to see if I could derive something neat, was I took that negative 1 to the n, because it doesn't depend on k, and I simply divided it to the other side. If you multiply both sides by negative 1 to the n, they cancel over here, and they end up over here. So I just turned this into log of k to the nth power, and then I had the negative 1 to the n come over here. But now what does this do? This actually allows you to very neatly define arbitrary derivatives of the Riemann Zeta Function, right? Because, at least where everything with real part greater than 1 is concerned. because now there's nothing stopping us from making n whatever we want. So we could quite easily ask ourselves, say, what's the half derivative of the Riemann zeta function? Well, all we have to do is plug in 1/2 for n. Remember, it's not dependent on k. This isn't running through the integers. So the first thing to notice is that the first term of the Riemann zeta function is always 1 in this definition, right? Because it's k to the, or 1 to the s power. So that's 1. We're going to assume for the sake of argument that s is real. I guess that's what it would have to be, right? Because then -1 to different complex powers is actually not, or 1 to different complex powers is actually not necessarily 1 all the time. But in the sense of the real numbers, we can actually eliminate it from the sum, because taking the derivative of the number 1 goes away. But everything else, 2 to the s, 3 to the s, those are varying quantities and they are not constant. So I suppose from every derivative onward we can sort of eliminate it. And you're going to actually see why we have to eliminate it when we consider some of the cases that we're going to take a look at. So first of all, we can consider the half derivative of the Riemann zeta function, which means we just have to plug in 1/2 for n. Well, what's -1 to the 1/2? That's, of course, I times the Riemann zeta function, but the half derivative of it. And plugging in 1/2 for that power just gives the square root. Right, so we have the sum from k equals 2 to infinity of the square root of the natural logarithm of k divided by k to the s. So for real s, the half derivative of the Riemann zeta function is actually purely imaginary, right? Because k is running through the integers, and if we allow s to be real, then we would have to divide both sides by I. We'd have -I on the right, which would mean that for all real inputs, the half derivative of the Riemann zeta function is purely imaginary, which is kind of interesting. But this isn't really the case that I wanted to look at. The case that I wanted to look at is even a little more interesting. It's a little more subtle, not subtle, I'd say, but it's cool. It's a cool little result. I don't know if you would call it a result. It's really just manipulating symbols at this point, but I think it's something that's worth considering and taking a look at because it yields two very interesting little series. So we're not going to do the half derivative or any of the integer derivatives. We're going to jump the gun and do the ith derivative. We're going to take the imaginary derivative of the Riemann zeta function. So we're going to have -1 to the power of I, which we will establish in a second, and the ith derivative of the Riemann zeta function, which is equal to the sum from k equals 2 to infinity of the logarithm of k to the power of I over k to the s. Now, what is -1 to the power of I? Well, quick aside, we know that -1 is also equal to e to the I pi based on Euler's formula, right? I've got videos proving Euler's formula is correct, so if you'd like to see that, that's perfectly valid. So if we raise both sides to the I power, that's like multiplying this power by I, so we get I squared in the power, but of course the power then becomes -1. And so -1 to the power of I is equal to e to the -pi, which is just brilliant. But I think that's just wonderful. And so that's what that is, and we can just replace it as such. So we have e to the -pi. One more manipulation we're going to do is we're going to replace the natural logarithm of k with e to the power of the logarithm of k, right? Because that's how logarithms and exponentials work. They cancel each other out, so that's perfectly valid. So we have k equals 2 to infinity of e to the, well, since we're going to have log of k to the I, we can bring I as a power out to the front. So we have e to the I, and this is the reason why we're doing this, log of k divided by k to the s. And now we can use Euler's formula to write this as cosine of the real part of the, the part that's being multiplied by I in the power plus I times the sine of it. So as it turns out, and then what we're going to do is multiply e to the -pi over, so we're going to isolate the ith derivative of the Riemann zeta function. So we're going to multiply both sides by e to the pi, and we get the conclusion that the ith derivative of the Riemann zeta function of s, why are my pens so running out? Oh, man, these pens, I just wish they lasted longer. I hate it. Okay, so I have to keep changing them. I'm going to keep changing them until I have no pens left. So the ith derivative, if that's visible, of the Riemann zeta function of s is therefore precisely equal to e to the pi times the sum from k equals 2 to infinity of the cosine of the log of k divided by k to the s plus I times e to the pi, so that little multiple of e to the pi simply gets distributed, times the sum from k equals 2 to infinity of the sine of the logarithm of k, divided by k to the power s. So we've got two very, very interesting little sums here. They're multiplied by a constant, e to the pi, which is about 23. It's just about pi plus 20. So if Papa Flammy's watching, then this is some good engineering fact here, right? E to the pi is exactly, if we're being engineers, it's precisely pi plus 20. Of course, if that were actually true, that would be an astounding fact, but it is not true. This is actually 23.04, not 23.14. But if you're an engineer, then this is theorem number, this is actually the ith and fundamental theorem of engineering. There's multiple. They actually have complex versions. Brilliant stuff, really. So the reason I wanted to show you this is because these two sums are very, very interesting looking. I don't really know much about them or how you would even manipulate them to find out what their values could be or whatnot, but I think they're cool on their own, and I think they warrant investigation. So if anybody in my audience wants to take a look at those and tell me any results they get, that would just be fantastic, because I'm not going to be committing any more time to them. And the other thing I wanted to show was, I remember Jens making videos about up rules for logarithms, right? So he did videos about, like, okay, so we know the rule of log of a plus b is equal to log of a, log of a times b is equal to log of a plus log of b, and he wanted to know what would have to be true, or what could I derive about logarithms if they worked in, say, like log of a plus b equals log of a plus log of b, as opposed to it being log of a times b. And the one that he mentioned that I think someone asked him to try, and then he said he had already tried, is this funky looking thing right here. If log of a times b, oh my god, these pens, man, pissing me off. Let's see if orange works. So if log, ooh, very vibrant. If log of a times b were equal to log of a times log of b, which simply is not the case, right? Usually it's log of a plus log of b is equal to this. Now, to find out more about this is sort of hard, right? From this point on, from here, it's a little difficult to really get at the issue. How would I solve for, like, a or b, right? In fact, I'll replace them with x and y, because we're going to end up solving for y. In terms of x, like a function, or some relationship between them at least. But the thing about wanting to see what would have to be true if this were true, that doesn't negate the previously known fact that this is equal to log of x plus log of y, right? That still has to be true, because it's always true for every x and y, which means we can reduce the problem of figuring out solving for y in this instance to solving for y in this instance, and that actually makes our lives much easier. So what we're going to do is we're going to raise e to both sides of the equation. E to the log x times e to the log y, which is just x times y. So we get xy over there. And we also get e to the log y to the power of log x, which is just y to the power of log x. So that becomes y to the power of log x. And all we're going to do now is divide both sides by y. So that just becomes that. And you know, we're actually going to keep x as e to the log x, and I think it'll be clearer that way. So now what we're going to do is raise both sides to the 1 over log x minus 1 power, and we end up with the result that y is equal to e to the log x divided by log x minus 1. And this is actually a really, really neat graph. It's its own inverse. As you can see in all of these relationships, you can swap x and y and there's no difference between them, right? You can swap those because summing is commutative, you can swap those because multiplication is commutative, and you can swap those because multiplication is, again, commutative. So it doesn't matter where the x and y is up here. So this is actually its own inverse. It's a very, very neat looking function. It looks something like this. It's a little strange, but it looks something like this. So it starts off at e up here and is like flat against the y-axis, and then it zooms down like that with pretty much a slope of -1, and then flattens up against the x-axis and stops at e again. So this point is 0e, and this point is e0. And then it's got this giant branch up here. So this is an asymptote, and this is an asymptote, but it's definitely one of those this is definitely one of those essential singularities, because it's completely different from both directions, right? It's not like This is definitely essential. If it's not, I'll eat my hat. But it looks like this. It's very strange looking. This point here, that's sort of like along the line y equals x, this is e squared comma e squared. And it's curious, like what might be the area under this thing, you know? This weird branch down here that goes from 0 to e. And it turns out the area under that is actually quite close to e. I think it's like 2.9 or something, or maybe even like 2.8 something. It's quite close, and as it turns out, if you do the integral, so if you take the integral from 0 to e of this function here, e to the log x over log x minus 1 dx, then it turns out that this is precisely equal to e squared times the integral from 0 to 1 of e to the 1 over log x, which is not an elementary integral. But still, so what that tells us is that this integral here has to be pretty close to 1 over e to cancel with one of the e's here to give us something that's pretty close to e itself. And I think this integral and this function are quite interesting to take a look at, because this function is actually just this function, but shrunk by a factor of e this way and shrunk by a factor of e this way. So it's actually a similar graph, a similar shape. It's just scaled up. This version is just a scaled up version of this one right here, but this is probably a more elementary version of the function. I say elementary, not meaning the integral, of course. But so this integral right here is something that I think would be interesting to investigate and maybe try and get a closed form on, or something like that, something similar. And that was really it. Those are the things I wanted to share. They're just cool little math things. This is something that Jens brought up, the little log rule that you're trying to prove. So if this is equal to this, then it must be the case that this is the function that you're looking for, this thing right here. I'll get that e out of there because that's kind of making it confusing. This function right here. And so that's Monday Math Nuggets for you. And I will have the Bernoulli stuff coming out this week. And then we're going to do, after the Bernoulli stuff, we're going to go into the complex iterations and bounded analytic hyperoperators, and I'm going to show you how you can extend the values or the heights of tetration to arbitrary heights, including complex numbers, which is quite cool. So we will have to take a look at that. Thank you very much for watching. I hope these little nuggets were enlightening in some way, and I hope you get something out of investigating them on your own. And I look forward to hearing any sort of conclusions you can draw about them. And if you think you've found something that's really interesting that you'd like me to put on the channel, or you'd just simply like me to know, then you can feel free to email me at whatthehectagon@gmail.com. The difference being, it's not hectagon, it's hectagon, because I misspelled it before I actually knew how to spell hectagon. And before I actually even knew it was a shape. I just kind of made the pun. Go me. Thanks, Google, for not letting me change the email, you stupid